opportunity to share some of the research we have been doing in Mexico already for several years. So I would like to combine several concepts that originated in cybernetics, which are requisite variety, autopoiesis, and self-organization. And first I will give a rather broad introduction to different topics related to complexity, and then I will start relating these ideas with requisite variety, with autopoiesis, and trying to bring it more into practice with some of the work we have done applying self-organizing systems into practical problems. So the talk will go from the theoretical to the applied and back to the theoretical. And let's start with a simple question. What is life? And there are many ideas of what is life. Let's see an example of a white blood cell chasing a bacterium. So we could say it's just a bunch of molecules, but somehow that bunch of molecules can detect where a bacterium is, and the bacteria can detect where it's being chased and tries to run away. So if we look only at the material components of these systems, of the molecules, we wouldn't say that they're alive. So how can we distinguish molecules, the same molecules which are not part of a living system, from those which are part of a living system? If we take our molecules and just separate them, what is lost? Life is lost, of course. But then what's the characteristic which makes life? And several decades ago, people realized that life is not only a property of the substrate, of the material and the energy, but it's also a property of organization. And it was precisely in cybernetics that was the first scientific descriptions of phenomena independent of their substrate. So using the same language, the same formalisms, people started to describe systems, biological and technological, using the same language. Therefore, focusing not so much on how systems are constructed, what are their components, but how these components are organized. And cybernetics has permeated into all disciplines. And now everybody speaks about systems. And more recently, the science of complexity have continued this tradition, looking at phenomena from a functional perspective, looking more at their organization rather than their implementation. This has allowed us to have a common language and also to share different models across disciplines, in physics and biology and sociology and economy. And there are different understandings of what complexity is. This would be one notion of what complexity is, which is Metro of Mexico City in rush hour. Well, that's to give you an intuitive notion of what I mean by complexity. Now, we can go to the etymology of complexity. It comes from the Latin plexus, which means intertwine. Why something is intertwining means that the components are difficult to separate. And what makes something difficult to separate means that the interactions between the components of phenomena are relevant. Why should they be relevant? Because interactions could determine the future of the components, therefore of the system. Traditionally, science has been reductionist, more by necessity than by choice, and that has been very successful. Most of the technological and medical advances we have used a reductionist approach which tries to simplify in order to predict. However, there are many phenomena around us and many global problems which cannot be reduced to their components. So, for example, if we look at our Google friend from school, Juan, and we know very well what is his behavior, we could say that we have a perfect model of his behavior. We know what he eats, how he dresses, which type of music he listens to. Then Juan suddenly gets married with Maria. We start noticing some changes in Juan. We cannot explain them. However, we notice that suddenly his behavior does not fit with our model. He starts behaving differently, using a different language, listening to different music, taking showers more regularly. And we would not be able to explain this if it wasn't, if we don't put attention on the interaction he's having with his wife. And if Juan and Maria have children, this will not only generate new interactions, but will also change the behavior and the future, the state transitions of the persons. It also will change the interaction between Juan and Maria. So, what I want to show with this example is that if we focus only on Juan, we will not be able to understand his behavior if he's not considering all the people, all the relevant interactions around him. And of course, these are not restricted to his family. And if we have problems describing a single family, how could we attempt to describe, model, and predict a whole society? And it's not a coincidence that the scientific study of complex systems has occurred in parallel with the development of digital computers. Why? Because we cannot study complex phenomena with pen and paper, with a blackboard. We just lack the computational abilities to consider thousands and multiple variables at the same time. However, computers, as Hans Pagels suggested, are akin to telescopes and microscopes, because just like we cannot study galaxies without telescopes, and we cannot study microbes without microscopes, we cannot study complexity without computers. And also, taking a phrase from Steve Jobs, where he says that computers are like bicycles for the mind. They are tools which enable us to explore phenomena which we were not able to explore before. That's why it's so relevant, the study of complexity, and it's so recent, not so much because people before didn't realize the relevance of interactions. And why are these interactions relevant, and why it's important to acknowledge? Because traditionally a reductionist perspective, which was required in science, carried implications which made us believe that the world was predictable. The mission of science was to find the laws of nature in order to be able to control and predict the future. However, if we have interactions that affect systems, we cannot predict how these interactions will generate information in the future. So, what we are taught in university from physics textbooks, that out of initial and boundary conditions we can predict the future of systems, does not apply for complex systems, because there is novel information, in some cases novel variables, which arise during the evolution of a system. Therefore, we cannot know the future before we get there. This is what Stephen Wolfram calls computational irreducibility. Now, there are many implications for these interactions, and I will not go into detail into these implications, which are more philosophical, but also within the cybernetics movement, Klaus Shannon proposed a measure of information, because this is precisely what is useful to describe interactions, actually not only interactions, but also matter and energy. The measure of information that Shannon proposed is akin to measuring novelty or randomness. So if we can predict the future of a system, knowing more, having more data about a system will not give us any information. On the opposite extreme, if we know nothing of a system, or if we cannot predict a system, meaning that the system is random, then each data point we get will carry maximum information. So a very skewed probability distribution will have very limited information, a very homogeneous especially from a materialistic perspective, can create some discussions. But emergence is really straightforward to understand. Emergent properties are those which arise at one level, at one scale, and not present at other scales. So life is one example of an emergent property because the components of living systems are molecules, and these are not alive. However, living systems, we say they are alive. Where does life come from? Well, out of those interactions. And we just say that this property, this information, these new constraints are emergent because they are not present in the components of the system. Let me give you an even simpler example. We have hydrogen. We can know all about hydrogen. A full description of the molecules of hydrogen. And we can do the same for molecules of oxygen. However, the properties of those gases will give us very little information about the properties of water, of a water molecule. Where do these novel properties come from? From the interactions between the atoms. And again, if we take several molecules of water, we will not be able to predict what will be properties of large masses of water, such as temperature, color, conductivity, that are present in the collective. So we can call these properties emergent. Let me give one final example, which is money. Money is not material. Why? Because it's not in the dollar bills, it's not in gold, it's not in the bits which carry electronic transactions. It's an agreement, it's a social agreement. So we cannot describe money in terms of physics. However, money being a social agreement has a causal effect on matter and energy. Simply this building required money to transform the matter which makes its walls and its ceiling. Thus, we cannot explain the transition of the matter which composes this building only from a physical perspective. Therefore, we need to consider interactions. This implies that interactions and information are as real as matter and energy. I don't really know what reality is, but having a causal effect on matter and energy forces us to consider them in our understanding of the universe. A complementary property of emergence is self-organization. Let me show you a video which illustrates this. And self-organization is commonly seen in collective behavior of animals, such as flocks of birds, schools of fish, stampedes, also in crowd behavior. There's no simple leader, however, they're able to coordinate the movements. This was very difficult to understand before we actually built computer models of collective dynamics, because if we try to model this with differential equations, we cannot solve the differential equations because there are just too many variables. We can see self-organization as the opposite of information. Why? Because sharing information is equivalent to Boltzmann entry. Why? Because having more disorder in the thermodynamic sense gives you more information. And reducing this entropy, this disorder, is precisely what gives you organization. And there's an analogy between emergence and information, because actually Shannon proposed information as a measure of novelty. We can say that emergence are properties which we don't know beforehand, therefore, if there is more information, we can use that as a measure of emergence. There are more details about these measures that we developed with Nelson Fernandez here in these papers that are indicated in these slides. And following Lopez Ruiz and his collaborators, just one final note about collaboration, about self also the inverse of channel information or entropy. And following Lopez Ruiz, we see complexity as a balance between order and chaos, between stability and change and variability. Emergence gives us change and self-organization gives us stability. Therefore, if we multiply emergence and self-organization, we get a nice and simple measure of complexity which we have applied in different domains. Now, let me go into the topic of the talk, mentioning Ashley's law of requisite variety. Actually, Ross Ashley was also the person who introduced the term of self-organizing systems in its modern usage. And the law of requisite variety is quite intuitive. It was proposed for control systems, but it can be applied to many other systems. So, Ashley says that in order for a system to control a phenomenon, it has to contain as much variety, at least, as the phenomenon it wants to control. Why? Because if the control has, let's say, 10 states, then the controller has to distinguish those 10 different states in order to be able to act accordingly. This applies to active control. Passive control does not require variety. And let's say this law can be summarized with the phrase only variety destroys variety. We have lots of options. We need a controller which will be able to respond to all those possibilities in order to adapt to different situations. And we can relate variety with information, because precisely the more variety we have, the more information we have. We can also relate it to complexity, because having different complexities of a controller requires different complexities of what wants to control that complexity. So this was generalized by Daniel Baryan to a law of requisite complexity, which states the same as the law of requisite variety. If you want to face the complexity of a certain system, you need as much complexity as that system in order to be able to balance that complexity. And it should be noted that this complexity and this variety are dependent on scale, because some organizations, for example, some work we're doing with the Mexican healthcare system, there are several institutions and these have relatively low variety. So you need one type to control at that scale. But at a lower scale, let's say at the scale of hospitals, you have huge variety because there's lots of information, lots of variety. Every time there's a different situation, because you have different patients coming into different departments. So you need to match the complexity of the problem at different scales. And this, the ideas of requisite variety were applied by Stafford here, as many of the speakers have already mentioned. And Stafford here related variety with the concept of viability. Why? Because a viable system has to fulfill the law of requisite variety. If it doesn't have enough variety to withstand the environment changes, or the environment it tries to control, it will not be viable. Why? Because variety will destroy the system. And this also applies to living systems, because we can describe living systems as control systems that try to have certain control over the environment. And in terms of the law of requisite variety, we can say that living systems require to have as much variety or complexity as the environment, otherwise they will not be viable. And Autopoiesis, as we have heard already, was proposed by Maturana Varela in the 1970s as a proposal to define the living. Etymologically, autopoiesis means self-production. So a system which self-produces, in the context of biology, could be called autopoiesis. However, this was extended by Luhmann and others into the social sciences. And if we take a perspective from information, then self-production does not apply only at material and energetic production. It also as information production. And it's also related with the concept of autonomy. So we can start relating the law of requisite variety with complexity, with autopoiesis, with viability, and with autonomy. And it actually can be measured with the concept of life ratio, which is basically how much of the complexity of a system is determined by itself as opposed to the complexity of its environment. And let me try to bring these ideas into application to give you a more intuitive and useful view of what I mean. And already for several years we have been using the concept of self-organization to design and control systems. Why it's useful to use self-organization to control systems? Well, you have a well-behaved, so to speak, system where you can find an optimal solution, and you find that solution and solve the problem. However, many problems are what we call non-stationary, means that they change in time. You have a problem changing in time, and the optimum changes faster than the speed at which you can optimize it. Your solution will be obsolete. Therefore, you need to adapt rather than to predict. And especially if we are facing complexity, where interactions are generating novel information, you have limited prediction. Therefore, even in spite of prediction being desirable, because you can react to perturbations before they occur. And this is desirable because perturbations can damage or destroy your system. With complexity, we know that we cannot do this all the time, so it will be better if we know what can we predict and what we should adapt for. And self-organization is a way of building adaptive systems, because instead of trying to build a solution for a problem which will be obsolete before it gets implemented, we design the elements of a system which will continually seek, by the interactions and constant sensing, the solution of a system, but then the solution of a problem. And then when the problem changes, they will reconfigure by themselves and find a new solution. Let me give you an example with some of the work we have done with self-organizing traffic lights. Now, let me change the color of the cars. So this abstract city simulation. And little squares represent vehicles. And we have a regular grid with non-orientable boundaries. And right now the traffic lights are coordinated with a centralized controller, which is used in most cities, also known as the green wave method. So if you see, once the vehicles get a green light, they don't have to stop because the green lights are coordinated to match the expected speed of the vehicles. However, mathematically, you cannot coordinate in four directions unless your blocks are something like 1 kilometer long, which we don't have. So if you go in the opposite direction of the green wave, then you have to wait every now and then, because you face anti-correlation of the traffic lights. However, if you increase the density, even the vehicles going in the direction of the green wave will not be able to go as fast as expected. Because in order to set up the coordination of the green wave method, you need to assume average traffic flows. However, traffic flows change constantly in cities. Of course, this is better than not having any coordination at all, but it's not adaptive. And in real cities, this problem changes at scales of seconds. Therefore, it's more efficient if you can devise a system which adapts at the same scale, which matches the complexity of the traffic dynamics. And, well, we see that we can enter quickly a video. Now, self-organizing traffic lights follow simple rules. So, similar to flocks of birds where there's no leader, each traffic light has local sensors and basically gives preference to the street with more demand. If I remove a parameter, so now there are no, I kill the sensors. Of course, if you don't have sensors, it will not work. So, directions with few demands will have to wait more than directions with more demand. But while vehicles in streets with low demand are waiting, there's a probability that more vehicles will join that demand. And this promotes the formation of platoons, which now you cannot see because of the color. So, these platoons, once they reach a certain size, they can request the green light before they reach the intersection. So actually, they don't have to stop unless there is another platoon crossing in that moment. But of course, in our cities, we never have such traffic. So let's increase a bit the density. And for this density, we see that there is a different regime because there is always demand at every intersection. However, the traffic lights are able to adapt, and there's a maximum flow because there are always vehicles crossing streets at every intersection. There's no time wasted. You cannot get more flow out of this topology. So this is as good as you can get for this density with this city. Of course, if you increase the number of streets or the lanes, you will get more cars in the streets. But let's get a more realistic density. Like Friday night in Mexico City after rain. So as you can see, there is still some flow. Most of the cars are stopped, but in a similar way as you have platoons self-organizing for low densities, for high densities, you have groups of spaces which self-organize and move in the opposite direction of the traffic flow. So when a car gets the chance to advance, they will do it for 100 meters or so. So this is also more efficient in spite of having an extremely high demand. So we have studied the dynamics of the system. We have identified different dynamical phases. Actually, there are 7 different dynamical phases for this topology. For other topologies, there are 10 dynamical phases. But here you can see the performance. So this would be the speed, this would be the flow. The flow is how many vehicles are moving through the system. So you have few density here. You have almost maximum speed. Cars almost do not have to stop. But you have also low flow because there's lots of free space. And as you increase the density, you increase the flow, the speed reduces, and then you reach maximum flow, and then the speed starts becoming saturated and the flow is reduced. Because if there's no space after a traffic light, both lights get a red light and they have to wait until space is available. And that's why there's this promotion of groups of spaces flow. And with the measures I sketched based on informational theory, we studied what is the emergence, the self-organization, and the complexity of the traffic lights and also of the traffic demand. So that is based on the switching of traffic lights. So the green wave method has regular switching of traffic lights, therefore it's predictable, therefore its information is zero, there is no emergence, therefore there is no complexity. Because you can predict it. So it's this manner. We can see here in the graph for complexity that the self-organizing traffic lights reach a high complexity for almost all densities except here. And why? Because for these densities, the traffic flow becomes regular. This is the information metrics for the car intervals at the intersection. This is the complexity of the cars. So we can see the traffic lights as the controller, and the cars as what they are trying to control, or their environment. And then we can compare their complexities. So we can see that for almost all cases, the traffic lights match the complexity of the vehicles, which is not the case for the green wave. The green wave method has high complexity of cars, just like for the self-balancing method. However, when it's gridlock, of course, there's the traffic flow, therefore there's no complexity. However, if you manage to keep traffic flowing, you will see that for these densities where you have maximum flow, the complexity is reduced because there's always traffic across all the streets. Therefore, the best approach is not to have maximum complexity. The best approach is to match the complexity of the system you're trying to control. And this can be measured with what we call autopoiesis from an information theoretic perspective, which is the ratio of the complexity of a system over the complexity of its environment. So we can measure it here, and if the complexity of the environment is greater than the complexity of the system, we can assume that the system is not viable and is controlled by its environment, and it does not have the requisite variety to face its environment. I didn't put the green wave method because it was always zero, it has zero autopoiesis because it has zero complexity. And self-organizing method, as it changes its complexity values according to the complexity of the cars it's attempting to control, for almost all densities, the complexity is higher than the complexity of the environment. And this curve shows how much we could improve from the theoretical optimum in this scenario, which is close to the phase transitions. So we can take this analogy and say that the traffic lights are better because they have properties similar to living systems, meaning that they have a higher complexity than that of the system they're trying to control at all scales and for all densities. And if we take this approach of describing life as information, as it has been proposed by several authors, we can apply our understanding of living systems not only to biology, but towards a general biology. And of course, this has been promoted by the artificial life community, not to study only life on Earth, but to study, on the one hand, life outside Earth, because the people working in exobiology, which is the search for extraterrestrial life, like in comets or in Jupiter moons or in Saturn moons, how do you measure it? How do you define it? I mean, if you look at the chemical components, it might not be life. You could get, in principle, similar components and not have living systems, or you could have living systems but not based on carbon, maybe on silicon or some other chemical basis, but working at different scales. Therefore, if we understand life as information, we can try to see not only life as it is, but life as it could be, as Chris Langton proposed. And this is useful not only for general biology, but it's useful for all disciplines, especially for technology and for sociology and for economics, because if we can build systems which have the properties of living systems, then we'll be able to adapt to their changing environments. Why? Because precisely living systems fulfill the law of requisite variety. How they do it? Well, they do it in different ways, and we can learn from how living systems do it in order to build more living artificial systems, more living organizations, more living economies, more living cities, which will be able to face the complexity of their environments, of their problems, of their constitutions. And we can also go a bit further into describing not only life, but the world as information. This idea began because many physicists have tried to describe information well, basically meaning in terms of matter and energy. So for example, in this video of the leukocyte, the white blood cell, chasing the bacterium and the bacterium trying to run away, physicists try to describe that type of dynamics from physics, from a physics perspective, in terms of thermodynamics. And it's very difficult to achieve that if you don't introduce meaning. I mean, what is the meaning of the chemical signals of the bacterium so that it will have a runaway behavior? However, if, let's say, you cannot get to meaning from physics, but you can get to physics from information. Why? Because we can describe matter and energy in terms of information. And this allows us to explore general laws of information, how complexity evolves in the history of the universe, how life could have emerged from non-life, and how can we better take our place in the universe. So, just to wrap up the different concepts I mentioned, I think that the work which was proposed within cybernetics by Ashby, by Beer, and many others concerning the viability of systems is still very current, and we should apply it to the systems we're trying to regulate, to build, to coordinate. Because we have the theoretical tools, but we still don't apply them. By we meaning our societies, our politicians, our communities, are still working on trial and error when there are proven solutions at hand, where there are concepts which are successful. And what type of tools can we speak about? Can we speak about living systems? And they're successful because they're here after billions of years. That's good enough proof for me. So we should try to build viable systems. Let's say systems which have enough requisite complexity to that of their environment. We can do this with self-organization, but also with other techniques, because we can, as we saw with the example of the traffic lights, self-organizing systems are able to adjust their complexity to the complexity of the problem that they're facing. And we can see autopoiesis as a life ratio, not only to try to define the transition between the non-living and living, but to try to apply it to different phenomena, to organizations, to societies, to cities, in order to seek the properties of living systems in these other scales, so that our societies, our cities, our governments will be more adaptive, learning, evolving, self-organizing in a robust way. And what we have seen is that we can guide the self-organization of a system to increase its autopoiesis. Why? Its complexity is a balance between emergence and self-organization. We see emergence as change and self-organization as stability. If you have too much change, you will destroy the solutions you have already. If you have too much stability, you will not be able to adapt to normal situations. So you need a bit of both. And emergence, let's say, change, entropy, we have for free. So we can use self-organization to try to match the amount of variability of our systems, to match the complexity of the problems we are facing. What I want to say, if we have very few variability, then we just need few self-organization to match the complexity of that phenomenon. We have too much variability, we need lots of self-organization to complement that variability and to increase the complexity of that system. And I think this is leading us to create what many people have described as living technology, not only let's say digital technology, because I mentioned urban systems, social systems, economic systems, which have all the properties of living systems. Thank you very much.
with some questions. Would anyone like to ask Carlos a question?
Hello, thank you for your presentation. I want to ask if life ratio can be used as a measure of freedom in a community or individual.
Yeah. I hadn't thought about that. I think it could be because say there's some analogies between freedom and autonomy, and indeed this can be seen as a measure of autonomy. However, what we have seen in some of our research is that you could assume that having total independence is the best for a system, or the best for an individual, and that's not always the case. So one of the things I realized a few years ago is that fitness is different from satisfaction. So let's say freedom could be understood as doing whatever you would like, whatever you would be satisfied with. And there are plenty of examples where people doing whatever they want for their own benefit is detrimental for the society. The tragedy of the commons. So, let's say, give another example from urban mobility. If everybody could take whatever route they wish, let's say, not agreeing on the directions of the streets, then it would be chaos because people would be running into each other. Let's say we have an agreement which says, okay, in these countries we will drive on the right hand, in these countries we will right on the left-hand side, and this restricts our freedom to ride wherever we want, but it makes traffic possible. So, in a similar way, as systems become more integrated, the components start losing their freedom, and this leads to meta-system transitions. However, once a component is integrated in a greater system, the system will take care of the survival of the components for its own good. So, in many cases, it depends which scale we want to improve. Scale at the individual scale, the community scale, the national scale, the scale of our species, the scale of our planet. And depending at which scale we try to improve, we will see that in some cases we will have contradictory situations. So for example, what is good for the economy might not be good for the environment, or also what is good at the short time scale might be detrimental at the longer time scale. So it's a very interesting question because yes, you can use it to measure something like freedom or autonomy, but it's not a given that these measures will tell you what to do. You always have to contextualize this information.
Thank you for coming and for your very good presentation. You said that we live in the world of information. I think that there is also another thing that makes particular this age and this world, and it's the communication. You can now communicate that information to almost everyone and everywhere. And you show us like how information can help to complexity, or how information about the complexity can help us to move to the autopoiesis. But I think that in the example of the green and red lights, the communication was kind of implicit because green and red lights just was the communication way, and we always have that. But how do we study the another communication ways that I think are really important to achieve the autopoiesis? Because in the birds video, we don't see any communication ways, but they are there. They are there. And how do we study that communication ways? Because not only the information is important, you can have a very valuable information. But if you don't have a communication channel appropriate to that, you may not transmit anything. So how do we study that?
Yeah, I did mention there is no communication between the traffic lights. Each traffic light is completely independent. However, information is transmitted through the vehicles themselves. So instead of one traffic light, one intersection telling the other, oh, you should expect this number of vehicles in a certain time, they just detect that. So the information is carried by the vehicles. So it's a stigmergic information, just like ant colonies. Ants do not tell directly, oh, here is a source of food. They leave pheromone trails. And stigmergy is communication through their environment. So another ant goes and picks up that trail. And we also use that with books, with internet, and let's say with external media, which allows us to transmit information, which is not only communication. What you mentioned, for example, with the flocks of birds, it's not, I wouldn't call it communication, but it's precisely interactions. Interactions is the transmission of information, but it's more general than communication, because it's simply the causal effect of one phenomenon over another. And I mean that's very general, so we can use many techniques in science. At the most general level, we can also use information theory to try to measure little information or transfer entropy in order to see how much information goes from one variable to another variable and how they are correlated. And let's say, as with the measures I presented, this has to be taken with care, because the measures will give you a number, but it will be up to you to make an interpretation of what does that mean.
Only one question. Could be consciousness in a crowd?
How would you define consciousness?
Consciousness could be a consciousness in a crowd, or in a fierce unit, or in a fierce organ unit.
Well, yeah, this is a hot topic, and I try to avoid speaking about consciousness, but let me give you a politician's answer. Let's say non-compromising. It depends on what you understand by consciousness. So, the most narrow definition of consciousness is human consciousness, which is restricted by the system embodying the consciousness, which is a human. Therefore, if it's not a human, then it's not human consciousness. So that would be the most restricted. Then the most general, if you see consciousness as awareness in the sense of being able to react, then almost any system would be said to be conscious. Just because, I mean, you could use it as a language game, but the bacteria is conscious of the leukocyte chasing it, no? Or a rock being conscious of gravity because it reacts to it when you let it go. However, I mean, you can do that. Then the question is how useful to describe a holding rock as conscious. So, let's say, going to the middle ground of a crowd, whether a crowd or even a society has consciousness, I don't think it's useful, well, I don't think it would be very useful to try to describe, yes, it has consciousness, no, it doesn't have consciousness, because the same word consciousness is used with different meanings. So for some meanings it will, and for some meanings it will not. I think it's more useful to say in which contexts or why is it useful to describe consciousness or crowd, and what can we learn from that description that we cannot from a different